All right, this is 14.7 now. Which this is where, if you've been following in this chapter 14, we basically have been repeating a lot of the ideas of 21a and, in particular, like, limits, derivatives, right? Although we've been doing partial derivatives, right? But now we're talking about three-dimensional functions, right? So we're repeating. And so in 21a, right, that's a very similar type of problem would be to find all the max min points, right? Find all the relative extrema of a function. And in 21a, right, the way we did that was, of course, you took the derivative, found your critical numbers, set the derivative equal to 0, stuff like that. We have, the process is different here, okay? So let me just draw an example here so we can clear what we're doing. I'm going to use my mountain again. This equation, I have no idea what that surface looks like. It might have mountaintops, it might have valleys, it might have, maxes and mins and stuff like that. But how are we going to locate? So at the top of a mountain here would be a maximum, right? And let me put some. So the starting place is we have to find critical points. We still call them critical points, places where we could potentially have a max or a min. But it's a little bit different than 21a. We have two derivatives, right? We can take our partial with respect to x, partial with respect to y. But in order for us to be at a point like this, it's not that you need a horizontal tangent line, you need a horizontal tangent plane, right? At the top right here for you to be at potentially at a maximum or a minimum. Now, what that also implies then is we need to show that our slope in both the x direction and the y direction, both of those have to equal 0, right? They both have to be flat. So critical points, why did I do that? Critical points are where both f sub x and f sub y equals 0. Another way, the way the book explains this, which is the same thing as I'm saying, what vector is made up of f sub x and f sub y is your gradient vector, right? You could also think of it as if I took that vector and set it equal to 0, 0. This explains the same thing. The gradient vector equals the 0 vector. Okay. I just usually just don't even bother with vectors. I just know I'm going to be taking these two partial derivatives and trying to find out where they're equal to 0. So let's start with f sub x. 9x squared plus y squared minus 18x. F sub y, x is constant, so that'll just stay there. But then I'm going to bring the 2 in front, so I'd get 2xy minus 2y. And what often happens, here I don't see anything I can really do here for this one, so I'm not going to touch that one. But here I see some factoring I could do. I could take out a 2y, which leaves me with x minus 1. And so that leaves me with two possibilities here. My partial derivative in the y direction equals 0 either when y is 0 or when x is 1. Okay. Now, in order for us to be at a critical point, I need more than just my derivative in the y direction to be 0. I need to also make sure that I find places where both of these are equal to 0. Okay. One of the examples I always use to kind of convince why you have to have both of these equal to 0. Any skiers in the room here? Anybody ski? I'm not a skier either. I've skied a few times just trying it. And believe me, if you're not a skier, you learn how to stop. That's the first thing you want to learn if you're not a skier. You need to know how to stop. So if you're on the side of a mountain, if you're a skier, you know this. How do you prevent yourself from going down? You face your skis like perpendicular to the slope, right? And so could you imagine that could be like your f sub x is equal to 0, right? You put your skis in a way so that their slope is 0. But certainly I'm not at a critical point here like I am here, right? Because in fact, what will happen if I turn my skis in the y direction, I'm going to go downhill, huh? Okay. This is why in order to be at a maximum or a minimum, you need to have both of these equal to 0, not just one. Okay. So here's how we do this. We're going to go take cases basically. I know that if y is 0, f sub y will be 0. So let's plug that condition into f sub x. Okay, so I'm going to say if y equals 0, then f sub x becomes 9x squared. If y is 0, that's gone. And here I can do some factoring. I get x equals 0, x equals 2. So this gives me two critical points. One of them is 0, and the other one has an x coordinate of 2. We wouldn't have gotten either of these had I not let y be 0. So it's 0, 0, 2, 0. Oh yeah, by the way, critical points now are going to be an x and a y coordinate, right? In 21a, it was just an x coordinate, but in 21c, it's an x and a y coordinate. But there's another situation we could potentially get more critical points, and that's by letting x be 1. So let's try that. If x is 1, f sub x would be 9 plus y squared minus 18, which is y squared minus 9, which is going to give me plus or minus 3 as an answer. So two more critical points are 1, 3, and 1, negative 3. Right, I'm going to take my condition with x being 1 along with those two answers there. So we have 4 critical points for this surface. And the way we classify them, I think I told you this before, right? You could either have a max, you could have a min, or you could have, if your surface looks like this, right at your critical point, the tangent plane is horizontal there, but it's not a max or a min. We would actually call that a saddle point. That's why we wanted to know that graph. So your options are max, min, or saddle points. Here's where it totally takes a different look than 21A. In 21A, you had your critical points, just put them on a number line, test for increasing or decreasing. But for these, the only way we have to classify these is to use what we call the second partials test. To classify as max, min, or saddle, use second partials test. And the second partials test, you're going to take f sub xx times that by f sub yy and subtract f sub xy, your mixed partials squared. When you do that at these points, you're going to get a number, and we're going to call that number d. And the reason it's called d, you guys know this stuff now, it's actually comes from a determinant where you take f sub xx, f sub xy, f sub yx, f sub yy. Remember determinants for cross products? If you did the determinant of this, you would get this times this, which is right here, minus these two multiplied together. But remember, what do we know about f sub xy and f sub yx?
Equal.
They're equal. So rather than say f sub xy times f sub yx, they just take this one and square it because it's going to be the same. All right, I started us off with a pretty involved one because there's 4 critical points, but the reason I did this is because this one has everything. If you've got more than, some of them will only have 1 critical point or maybe 2. If you've got more than 2, I would make like a little table here. So here we're going to put our critical points. Here we're going to calculate D. I'll tell you about the last 2 columns here in a second. So we'll have, what were our critical points? There, 0, 0, 2, 0, 1, 3, 1, negative 3. And if it's not too terrible a function, what you can actually do is I'd like to do is put these derivatives right in here. So what is f sub xx? Here, I put the bottom here, so
18x minus 18.
good. F sub y is 2x minus 2. And then we're going to take f sub xy and square it. F sub xy, partial of this with respect to y, looks like it's just 2y squared. Okay, so let's start with 0, 0, and then I'll tell you what these other 2 columns for. So you literally just run these through. If you plug in 0 for x, you're going to get negative 18 times negative 2 minus, this is going to be 0 squared. So you end up getting positive 36. The 36 isn't as important as the fact that this is positive. What happens if D comes, so this is going to be your conclusion here on the last column. If D comes out, there's rules for this. You can find them in the book and everything, but I want you to think, this part you can think through logically. As long as you know this, that if D is greater than 0, then it's either a max or a min. It can't be a saddle anymore. It's either a max or a min. And here's how you tell. If you look at, let me rewrite it here. Remember, this represents f sub xx. This is f sub yy. And we talked about those when we did partial derivatives. That's measuring the concavity, right? And what this is saying is at 0, 0 on our surface, both f sub xx and f sub yy are negative, which means our graph is concave down in both the x and y directions, right? So if you knew it was either a max or a min, but you knew the graph was concave down like this, what would you be inclined to say, a max or a min?
Max.
That looks like a max. Yeah, it's going to be a max. So what the book tells you to do is they tell you to look at the sign. I'm going to put the signs of f sub xx. You could actually do either one or both. If D comes out to be positive, these have to be the same sign. They have to be either both positive or both negative. So the book basically just tells you to look at the sign of f sub xx. And since it's negative, that tells you it's concave down, which makes this a relative max. So how about here? I put either max or min. Rather than memorizing the formula, I'm going to say, look at the concavity. Look at both f sub xx and f sub yy. All right, let's try 2, 0. 36 minus 18 comes out to be positive 18. 2 times 2 is 4 minus 2 is positive 2. And y is 0. So this gives me also positive 36. But the difference is now both f sub xx and f sub yy are positive. That tells me the graph is concave up in both directions. So then this one would be a relative min. At 1, 3, oh gosh, if x is 1, this is 0, isn't it? That's 0 times, actually, who cares? It doesn't really, well, it's 0 times 0. Minus 2 times 3, 6 squared. So minus 6 squared gives me negative 36. This is a bad example to explain why this is true, but let me show you a better example. One of the ways d will come out to be negative, besides this one, is that let's say on a different problem I had f sub xx coming out to be positive 7, f sub yy came out to be negative 2, minus something squared. Do you see that? And this would be f sub xx, this would be f sub yy. If this is positive and this is negative, this is going to come out to be negative. And if I subtract anything squared, do you see how this is guaranteed to come out to be negative? If these two have opposite signs, it's guaranteed to come out to be negative, right? There's no way you could get a positive number anymore. And this is easier to visualize because if these two had opposite signs, what that tells you is the graph, I need to move this up. In one direction, it's concave up. In the other direction, it's concave down. Well, what does that remind you of? That looks like a saddle, doesn't it? That's what a saddle looks like. It's concave up in one direction, concave down in the other direction. So it's more evident when you see that these guys have opposite signs. That didn't happen here. I mean, I guess for us at 1, 3, it was concave nothing in both the x and y direction. But what is still true is if d comes out to be negative, you don't even, this doesn't matter. It's automatically a saddle. Automatically a saddle. I'm pretty sure it doesn't, don't I get the same thing for 1, negative 3? I think I get a saddle as well. Okay. The good news is in 21A, you would have had to take this information and actually sketch the function. These are too hard to sketch without technology. So you don't have to, that's all you have to do is identify the maxes and mins. There is a third possibility, which I have some examples with this. So if d is greater than 0, you look at the signs of f sub x and f sub y, make your call. If d is less than 0, then it's automatically a saddle. And it is possible if the numbers work out just right that d could equal 0, in which case your test is inconclusive. So it fails. Let's see how to deal with that. All right, let's try another one. This one's maybe not quite as bad. Yeah, so start by finding f sub x and f sub y. And I just try to choose whichever one looks the easiest to work with. I think I like this because it's just linear. Did I do that right? Yes, I did. If I set this equal to 0, that tells me that 2y equals 4x. So y is equal to 2x. See, I didn't get numbers here like I did on the other one, but I got a relationship. I got something out of this. And so to actually get a critical number, I know that if y equals 2x, then f sub y will be equal to 0. That needs to be satisfied. So I want to take this condition and plug it in to the other one. That's effectively what we did on the first example when I took those numbers and plugged them in. And so then f sub x becomes 8x cubed minus 4 times 2x. And so I get 3 values for x, plus or minus 1 and 0. So my 3 critical points, one would have an x coordinate of 0, 1, -1. And remember how we got all of these x values was under this condition, right? That y equals 2x. So your y value is going to be 2x. So 2 times 0 is 0. 2 times 1 is 2. 2 times -1 is -2. Okay, so then we're going to use the second partials test. I make f sub x equal to 0 and f sub. Yeah, because I need a horizontal tangent plane. Whatever this surface looks like at any place where there's a peak or a valley or something, I'm going to have a horizontal tangent. So f sub x and f sub y are both going to be equal to 0. I don't know what that shape is, but that's, yeah, so always want to do that to find your critical points. So knowing I'm going to need my second partial derivatives for my second partials test, let's just crank those out right now. I guess since I have 3 points, I'll still make my table.
Wouldn't 16x squared, yeah, be 24x squared?
What in the world was I getting 16 from? I was just checking to make sure you were all awake. You all believe that, right? Thank you. Okay, so then 0, 0 is probably going to be the easiest. Let's start with that. So you get -16 for that, which means that's got to be, it doesn't matter what's going on here. That has to be a saddle. Yeah, try the other two on your own. Actually, I think it's going to be the same for both of these, isn't it? Because if you plug in -1 for x, you're going to get 24 times 2 minus 16 is, it doesn't matter, right? That's positive. So then I look at the signs of f sub x. They're both positive, and f sub y. So I know this is a relative min, and I think I'm getting the same thing here. There, I was just remembering when I was thinking about what this, what was interesting about this problem. So this surface, right, which, okay, you know, there's no denominators. Would it be continuous? I would say yes, right? There's nothing you can't plug in for x and y. This is continuous everywhere, okay? And what we find is this thing has two locations where there's a minimum, right? Remember, in 3 dimensions, a minimum would kind of look like an upside down, you know, part of the surface looks like a bowl, right? You have 2 of those, and you have a saddle, okay? And a saddle, remember, is nothing, right? That's not a min or a max, okay? So, but what's kind of was an interesting question that one professor pointed out is, go back to 2D. For a continuous function, try to draw a function that has 2 mins and doesn't have a max. And I know this has a saddle too, but a saddle's not a max, right? Try to draw a function that has 2 minimums, a minimum and then another minimum. I mean, even if you make it go flat or something, you could call that a max still, right? And then another minimum. There's no way you could have 2 minimums without a maximum, right? But in 3 dimensions, you can, which is kind of cool. Not quite, Dylan. There's a little bit more to that. In fact, let's just go to this right now. How am I doing on time? Yeah, it's 4:04. Okay. So I think with 2 examples of this, you get the idea of finding relative extrema. Find your critical points, run it through the second partials test. You may recall from 21A, this is going to be a long problem here, I apologize. Let me show you the 21A equivalent. You may remember, this is scratch paper here, so you don't have to write this down if you don't want to. In 21A, there's something called the extreme value theorem. And what the extreme value theorem says is that if you have, of course, it has to be a continuous function on a closed interval, is guaranteed to have an absolute max and an absolute min. Okay. This was early on in 21A. So here's the idea. Try to draw a 2-dimensional graph of a function that has endpoints, right? Where you're always going to get a max or a min, right? So obviously if you do something like this, you know, on a closed interval, you're going to get a minimum at your endpoint. You're going to get a maximum right here, which would be a place where your derivative is equal to 0, which would be a critical point, right? And that was one of the things we learned in 21A, was that your extreme values always either happened at endpoints or at critical points. No matter how you draw the graph, even if you just draw it like straight line here, you're going to get an absolute min here, an absolute max there. And then, yeah, they always have the wise people in 21A. Well, what if I drew a horizontal line? And I'd say, well, there's your absolute min and your absolute max, right? The function, if it always has just one value, that's both your absolute max and your min, right? And it's always that value. So no matter how you draw the function, as long as it's continuous, it would be guaranteed to have an absolute max and min. Okay. And it would either occur at, I'll put at endpoints or critical points. Can't see that. That's where we would find them in 21A. So this is kind of the equivalent. Need some light in here. Get dark. But for functions of two variables, three-dimensional functions, if we get a function, if we look at it in its entirety, it may not have any max or min points, absolute max and min points, but this is the equivalent to like a closed interval. I need to explain what they mean by this. Over the triangular region bounded by y equals negative x plus 5, y equals 0, and x equals 0. What they're talking about here, let me first sketch that region. Okay, this forms a triangle if you graph this. What they're getting at here is here's what helps me visualize what's going on, because it's always hard when you can't really draw this exactly. So this region is in the XY plane here, right? If I sketch that three-dimensionally, this is a line that connects the X and Y axis. So like right here and right here. This would be 5, this would be 5, just like it is here. Now this right here is some kind of a surface. And let's presume that that surface is above, like if I graphed it, it's above this. So let's say this surface, do this. Okay, here's your surface. Here's your f of xy. I'm just pretending it's curving here. Here's what they're talking about, and here's the analogy that helped me think about this. Imagine you're in a room. I'm in a room right now. I suppose probably all of you are, right? The floor of my room looks like a rectangle, as most rooms do. So try to imagine you're in a room, and this is your floor. That's your floor right here. And this equation right here is your ceiling. My ceiling's flat. Mine's like a horizontal plane here, right? But imagine you had a curved ceiling, and then this is your room. So then imagine you had walls going straight up. This would be a wall, this would be a wall, this would be a wall. So imagine there was a wall going straight up until it hits the ceiling, right? Now, if you had a curved ceiling, hopefully you can kind of see that that probably means your ceiling is going to be kind of curved too, right? It's going to look like something weird like this, right? It's going to be a curved ceiling. Essentially, what we're looking for then is within this room, what is the highest point and the lowest point on the ceiling? That's what we're looking for. We're trying to find the absolute max min of the function itself, which is the ceiling, over this floor, over this region. Okay. The room analogy really helped me to visualize, like, okay, that's what I'm trying to find here, right? Now, where would we look to find the highest point in the ceiling? Well, depending on how the ceiling looks, the highest point could be, maybe this is like a curve thing. Maybe it peaks out right here, okay? If the highest point is within the middle of the ceiling, that's going to come out as like a horizontal tangent plane. That's going to come out as a critical point, okay? And we know how to do that. We just did that. If it's within the room, it's going to be a critical point. But where else could it be? I mean, I don't know what the ceiling, maybe the highest point is directly over this point right here, which back on my two-dimensional graph, that would be this point. Maybe it's directly on the z-axis. Maybe that's my highest point, right? So this is kind of like the equivalent to when I said in 21A, your absolute max can occur at critical points or at endpoints. Well, in 21C, the critical point would be like a horizontal tangent plane in the middle of the room. And I think of these, any of your corner points are kind of like the endpoints. Okay. But there's a third possibility. What if it just so happens that maybe along one of these walls, maybe it turns out, you see how my wall's kind of curving up like here? Maybe my highest point actually occurs right along this wall, right at the very edge of the ceiling and the wall. Maybe it occurs right there, which would be like somewhere along the wall here. We have to investigate all three of those options. Okay, these problems are tedious. So let me write down what we just talked about. So absolute max min points can occur at 1 critical points. We know how to find those. 2 corner points. We have all of those. And then 3 along, I call them the walls. Okay, so we have our 3 corner points, right? We have 5, 0, 0, 0. We'll deal with those later. And then 0, 5. So we've kind of got that. We'll check that out later. Let's see if there's any critical points for this function. So I'm going to do this. I'm going to use this space right here to see if there's any critical points. Critical points, question mark. We'd have to take f sub x, which is y minus 1. And we'd have to take f sub y, which is x minus 2, set that equal to 0. What's nice about this, so critical points have to be, I need an x and a y value that make both of these equal to 0. I've got it here, right? If I just join those together, I have a critical point 2, 1. Just in case so they don't try to trick you, make sure that that critical point is actually within your room. If it was way over here, I wouldn't care about it, right? I'm only carried, my universe exists inside this floor here. But 2, 1 is inside there, right? 2, 1 is like right there somewhere within my room. So that's a critical point. Now what we want to do is investigate along our walls. And here's how you do that. There's 3 walls there. So let's first check along. Which one do I want to do first? I want to show you, I want to take the hardest one first. Let's take the hypotenuse. Let's take along the wall y equals negative x plus 5. And what you do is you just plug that in for y in your function. So my function is going to be 3 plus x times negative x plus 5 minus x minus 2 times negative x plus 5. And then I'm just cleaning this up. It's plus 6x minus 10 is minus 7. Hopefully I did my math right. Now the way to visualize this, imagine you're in the room, you're sitting in that room. I need to go back up here to kind of see that. You're sitting in the room here on the floor and you're looking at this wall. And in particular, you're looking at the ceiling. And what this result is telling you is this ceiling right here looks like that graph, which is an upside down parabola, right? This is what the ceiling looks like if you're looking along that wall. Now, what am I'm looking for extreme values, right? I'm looking for maxes and mins. And a parabola has a high point, doesn't it? I'm interested in this point, in other words, along that wall. That's a point of interest. So I want to locate that point. How do I locate that point? Well, that's the vertex of the parabola. We can use our old vertex formulas, or we can go 21A style, right? There's a maximum when the derivative, which is negative 2x plus 6 equals 0, and that gives me x equals 3. Remember, y equals negative x plus 5 was the equation of our line, so y would be negative 3 plus 5, which is 2. So here's what we know. 3, 2 is a point of interest. Okay, so I want to remember this. And you know what I like to do is to go back to my picture up here. This is my personal thing. What we just checked this wall. 3, 2 is actually on this wall. I like to just put a little dot there because I know what I want to do. These are all my candidates for high and low points in this room of the ceiling. And so that's going to be added to my list of candidates. Okay. Now there were 2 other walls, and let me tell you about those. Let's do y equals 0. I'm going to use this room up here. Along y equals 0, if I plug in 0 for y, my function just becomes 3 minus x. Now, what does 3 minus x look like? That is just a line, right? That's just a line. Unlike a parabola, there's no extreme values here, right? No max or mins, right, for that. We're not really worried about that one. So check it off my list. I'm done with it. That leaves one more wall, which was x equals 0. And fortunately, if x is 0, my function just becomes f of y equals 3 minus 2y, which same situation. That's also a line with no max or min points on that one. 3 minus x, where did that come from? 3 minus x came from, plugging in y equals 0. I know it's hard because I got to zoom this all out. I plug y equals 0 into my function. And that would make this term and this term 0. Yeah. Okay, so here we go. I'm going to need another piece of paper. So I'm going to... Once you've investigated everything, we've got our critical point, we have our 3 corner points, we checked out the 3 walls, and we found out that the only wall that has a point that's interesting is the hypotenuse, which has that point 3, negative 2. So then what you do is you just get a list going of your candidates. I even literally call it that, candidates for the highest and lowest point. And then ultimately what it comes down to is we need to evaluate our function at all of those points. So I'm going to start with my corner point, 0, 0, 5, 0, 0, 5. My critical point was 2, 1, and my wall point was 3, 2. If x is 0 and y is 0, I'm going to get just 3. You guys can check my work. I believe this gives you negative 2. I'm plugging these back in here. Maybe I'll write my function here since I can't see it. It's 3 plus xy minus x minus 2y. Negative 7, I think. 3 plus 2 is 5. Plus 2 is back to 3. I think this is positive 1. 3 plus 6 is 9. 9 minus 3 is back to 6. 6 minus 4 is back to 2. If I've done my math right, those are the z values, right? Those are the heights, if you will, of the ceiling over these points. That's the height of the ceiling. Well, I know it's weird having a negative ceiling height. So yeah, but you get the idea. So then we can make the call, right? So now we can say that here is my absolute maximum. 3 is bigger than any of the other ones, and my absolute min was right here.